So let's go ahead and discuss a couple things that we weren't able to get to in lecture. Mostly, let's recognize and introduce the three types of intermolecular forces that you learned about in general chemistry. Then we're going to describe how you can analyze the factors that specifically affect the strength of the London forces. And then we're going to discuss briefly their relationship to boiling points and solubility. So first of all, let's just talk a little bit about the three major intermolecular forces. You have the dipole-dipole interactions. You have hydrogen bonding. And then you've got the dispersion forces. Now, they're not actually in the right order when it comes to the strength. The strongest forces are the hydrogen bonding. Then comes the dipole-dipole interactions. And lastly, you have the dispersion forces, also known as the London forces or the induced dipole forces. Those are the forces that come about merely by the random fluctuations of electrons within a molecule. So the dipole-dipole forces are specifically for polar molecules. If your molecule has a net dipole moment, then it can experience dipole-dipole interactions. If it does not, if it is nonpolar, then it cannot experience dipole-dipole forces. And what typically happens is there's an attraction then between the negative and positive ends of those dipoles. What we see here is an example of acetone. So acetone is a polar molecule. It has a net dipole moment with a negative end on the oxygen side and a positive end on the carbon side. What happens within a collection of acetone molecules is they are attracted to each other via their dipole-dipole forces. It's what gives a greater boiling point and melting point value to acetone compared to another molecule of a similar size. If we look at isobutylene versus acetone, we can see they're very similar in size, but instead of having oxygen here, isobutylene has a carbon, and that makes it nonpolar. So notice it has melting points and boiling points much lower than that of acetone because it has weaker intermolecular forces than acetone. The stronger the intermolecular forces, the higher the temperature has to be to cause these transitions, for example, melting or boiling. So hydrogen bonds are an especially strong type of dipole-dipole attraction or interaction. And it's because of the uneven sharing of the electrons between the hydrogens and the very electronegative atoms that they're connected to, creating much larger partial positive and negative charges, that they make the attractions that much stronger. Although there really is a very, very sharp cutoff about what's labeled hydrogen bonding and what's not. Hydrogen bonding has to occur between a hydrogen that is connected to specifically either nitrogen, oxygen, or fluorine, and then that hydrogen is interacting with another atom that is either nitrogen, oxygen, or fluorine. You can't have an atom involved, either the atom that the hydrogen's attracted to, or the atom that the hydrogen is covalently bonded to, not be either nitrogen, oxygen, or fluorine. Now, it doesn't have to be the same atom. In other words, if you have a mixture of compounds, you can get hydrogen bonding happening between water and ammonia because the hydrogens on the oxygen can hydrogen bond with the nitrogen because both of those atoms, oxygen and nitrogen, are one of those three atom types, nitrogen, oxygen, or fluorine. Now, once again, hydrogen bonds, even though they're called quote-unquote bonds or hydrogen bonding, it is not a bond. It is not a covalent bond. As you can see here, it's still about 20 times weaker than a covalent bond. So it's still merely what we call an intermolecular force, and it just holds the molecules together. They still remain their own molecules. They're not bonding and creating a new substance. Now, hydrogen bonding does create a class of compounds that we're going to talk about more later. And so solvents that can do hydrogen bonding are going to be called protic solvents, whereas solvents that do not do hydrogen bonding are going to be called aprotic solvents. So we see some examples. An aprotic solvent, like diethyl ether, it doesn't have any hydrogens that are able to do hydrogen bonding. It has hydrogens, but they're not capable of doing hydrogen bonding. Whereas acetic acid is protic because it has this OH. Now, dimethyl sulfoxide, it has no hydrogen attached to this oxygen. It has hydrogens, but they're connected to carbon. So the hydrogens are not able to do hydrogen bonding, therefore it is an aprotic solvent. Another trend is the greater the amount or capability of hydrogen bonding that's possible for a molecule, the greater the effect the hydrogen bonding has on holding the substance together in its state of matter. For example, we look at these three isomers. Their boiling points are different because there's more hydrogen bonding capabilities in propylamine than there is in trimethylamine. So it has a greater boiling point because there's a much greater hydrogen bonding effect. Now, when you have molecules that are nonpolar, they can still have an attractive force between each other. This is known as the London dispersion forces, and that's because these nonpolar molecules, they're nonpolar because for the most part their electrons are evenly spread out and evenly shared. However, there still is fluctuation, movement of the electron density around the molecule such that at any given moment there is an uneven distribution, or can be an uneven distribution of electron density. So some areas can be negative and some areas can be positive in a molecule. For a given moment of time, it's not always evenly spread. On average it is for nonpolar molecules, but not always at any given moment is it perfectly spread out. And so those momentary dipoles, momentary dipoles, they can then induce a dipole in another molecule nearby, creating this just brief induced dipole attraction between these two normally nonpolar molecules. And this happens temporarily, and then it goes away. So it's like these forces of attraction occur, and they attract, and then they let go over time. And they're just happening brief moments over time. And because it's at any moment, at any space on the molecule, we're going to find that this leads to certain effects that happen with London dispersion forces. These fleeting attractions, they're generally weak and momentary. However, just like any attraction, like Velcro, the more there are, even though they're fleeting, the greater the overall effect will be. And so one effect is the surface area of the molecule. The greater it is, the greater the London dispersion forces overall are. That's why as molecules get larger in their surface area, have a greater, more stretched out shape, they tend to have a greater overall intermolecular force, or due to the London dispersion forces. For example, Velcro I mentioned, as well as the feet of geckos. Their stickiness to the walls and such, these lizards, they're due to London dispersion forces, and yet they're able to support their weight because the molecules that are creating those forces on their hairs, they spread out over a wide surface area. What we see here is you look at butane versus pentane versus hexane, we're seeing that as you get to larger and larger molecules, even though they're all nonpolar, you're starting to see a much higher boiling point for hexane versus butane. And the reason for that is that the more mass a molecule has, once again, generally speaking, the larger it is, thus it has more possibilities for those momentary induced dipole attractions to form. The branching effect is really essentially what we mentioned with the surface area earlier. It's just an example of it. Pentane is more stretched out, so it has a greater amount of surface area where those induced dipole attractions can form at any moment. the more branched the molecule gets, the more compact it gets. Even though it's the same mass, it's more compact, it has less surface area, there's less opportunities for those induced dipole moments to occur when it has a smaller surface area. And then the last thing, we've talked about boiling points and melting points. The last thing we wanted to talk about is solubility. And it's, for this course, all you really have to remember, we're not going to delve deeply into solubility and mixing. You did a lot of that in GChem, but you just have to always remember the old standard, like dissolves like. So polar compounds generally mix well with other polar compounds, and nonpolar compounds generally mix well and dissolve other nonpolar compounds. Generally, a polar and a nonpolar compound don't usually mix well together, though there can be exceptions, especially if you use additives like soap. Well, that looks like it's it. Hopefully this video is helpful in giving you a good refresher on the intermolecular forces.